All right, so what I would like for us to do today, and it's my ultimate goal to get out of here a little bit early so I can go work on grading you guys' tests and all that kind of stuff so that you have something graded before the drop date tomorrow. But anyway, so my ultimate goal for today is to work a few more example problems related to what we were talking about with regards to transformers the last time we were able to meet. And then I'm going to wrap things up with energy storage in transformers, which will be related to the last problem that we have here. Okay, it seems to be back. All right. So for this first problem here, we are asked to essentially figure out what our output voltage is V out using the input impedance method that was discussed in class last Thursday. Okay. So this circuit is going to be a little bit different than I think things we've done in this class, in as much as I am asking for the time domain output voltage, and I gave you a time domain signal. So anytime that we see a circuit that contains, resistors and then capacitors measured in some type of farad and inductors measured in some type of Henry, we need to first convert this into the frequency domain so that we can do all of the normal circuit analysis that we've been doing, right? So you guys should be aware of these relationships, and we have actually used them in this class before, but I'm just going to remind you that the impedance of a resistor is just the resistor value itself. The impedance of an inductor is given by the expression J omega L, and the impedance of a capacitor is given by 1 over J omega C, which is the same thing as negative J divided by omega C. And for those of you who may not remember, our angular frequency omega is just whatever is being multiplied by time inside of our sinusoidal excitation function. So in this case, our angular frequency is 2000 radians per second. Okay. So the first thing I might do is redraw this circuit in the frequency domain. So do you guys remember how to get phasor voltages from a time domain voltage? So it's actually quite simple. All we have to do, and this is something that you should have learned in the ENGT 221, is we take the magnitude of our time domain voltage, we take the phase angle of our time domain voltage, and we throw everything else away. So this 50 cosine 2000t plus 0 degrees would simply become 50 angle 0 degrees volts, right? We kept the magnitude, we kept the phase angle, we threw everything else away. Is that particularly difficult? I don't think so. Have you guys seen that before? I hope the answer is yes. You should have covered it in your circuits class. Okay. There is no phase angle here, so that's just an implied plus 0 degrees. So you might see something, like 50 cosine 2000t plus 25 degrees. The phase angle will be 25. This is plus 0. So, yeah. Since the impedance of a resistor is just the resistor value itself, that 10 ohm resistor continues to look like a 10 ohm resistor. Now we have our 25 microfarad capacitor. So I'm just going to throw this into my calculator really quickly. So I'm typing in 1 over 1i times our angular frequency of 2000. And then we have a capacitance of 25 microhenry. Does anybody remember what the prefix micro means? 10 to the negative 6, absolutely right. So 25 times 10 to the minus 6, and I wind up getting an impedance of negative J 20 ohms. Now we'll have our 3 millihenry inductance for our coil. So here I'm using the expression J times omega times L. So in my calculator, I'm doing 1I times 2000 times 3 times 10 to the minus 3, because a millihenry is negative 3. And I get an impedance of J6 ohms here. Putting dot on this side. For this 10 millihenry inductor, I'm once again just going to use that J omega L expression. And so I'm just going to replace the 3 for my previous thing with a 10. And I get positive J 20 ohms. For the capacitor, 1 over 1I times 2000 times 10 times 10 to the minus 6 gives me a negative J 50 ohm impedance. My 50 ohm resistor continues to look like a 50 ohm resistor. I'm now going to be finding a phasor voltage V out. And lastly, I need to come up with the impedance for my mutual inductance. So that's 1I times 2000 times 1 millihenry. And that looks like a J2 ohm impedance for my mutual inductance. Okay. So if you were to look back at our notes for what we did in class on last Thursday, where we were calculating the input impedance, when we derived everything, we had our mesh currents for both of our loops as flowing into the positive polarity terminal, or into the dotted terminal of our coils. So that's how I'm going to essentially define things here as well. So I'm going to wind up saying that this is my mesh current I1, oriented in such a way that it's flowing into the dot, and this is going to be my mesh current I2. Okay. So if you recall, our input impedance Zn was given by essentially our primary loop impedance plus the magnitude of our mutual impedance squared divided by our secondary loop impedance. So for this particular circuit, what is our primary loop impedance? So what impedance do we see as we follow that mesh current I1 around? So how do those two combine together? Negative J14, right? 6 minus 20 is negative 14. Throw the J's back in. Okay. So I'll write that as 10 minus J 14 ohms. Are we all okay with that? I usually put the real part first and the imaginary part second. Okay. What is the magnitude of the impedance of the mutual inductance. So the magnitude, we're going to throw the J away. So it's just going to look like 2 ohms. And then what's our secondary loop impedance going to look like? 50 minus J30. Absolutely right. And so I'm just going to now throw this into my calculator, right? So 10 minus 14J plus 2 squared over 50 minus 30J. And when I put this into my calculator, I got 17.210 with an angle of negative 54.234 degrees ohms in polar form. And I'll go ahead and convert that into rectangular form as well. And I got 10.059 minus J 13.965 ohms. All right, so from this primary loop impedance, which we found that matches the answer provided, how would we go about step by step winding up solving for the quantity V out? Anybody have any thoughts on that? So it'll be V out is going to be I2 times negative 50 ohms. And I'm saying negative 50 ohms because the current is flowing into the negative polarity terminal of that voltage. So in order to calculate that V out, then we need to figure out what I2 is. Well, how do we figure out what I2 is? Do the circuit. Absolutely. Just like we did last time. So that's really what I'm looking for there. Yeah. So we're going to find I1, write a Kirchhoff's voltage law equation around that primary loop, because that will be how we tie I2 into known quantities. And then once we know I2, we'll just use Ohm's law to solve for V out. Okay. So how would we find I1 then? I1's on the primary loop though. Has nothing to do with any of those impedances. Yeah. So in our last example that we worked, we simply took 50 ohms, or our source voltage, and divided it by our input impedance. Okay. This is going to be slightly different. Okay. So I'm going to do something similar here, right? I've got my source voltage of 50 angle 0 degrees volts, and I'm going to have my input impedance of 10 minus 0, 10.059 minus J 13.965 ohms. What I'm going to do here specifically though, is I'm going to put a negative sign. And the reason why I'm going to put a negative sign is because in our last example that we worked, our current I1 was flowing in the opposite direction, right? So we did everything under the assumption that the current was leaving the positive polarity terminal of our voltage source we've defined I1 as the current leaving the negative polarity terminal, which means we just need to change the direction. So we would have negative 50 divided by my previous answer, and I just got a current of 2.905 with an angle of negative 125.765 degrees amps. So before I move on from this step, does anybody have any questions, comments, or concerns about where this relationship came from, or particularly why we're using a negative sign? All right. So now that we know what I1 is, if we write a Kirchhoff's voltage law equation around mesh 1, that will involve mesh current I2 because of the mutual inductance between those coils. So just to be clear here, I'm going to assume that the positive polarity terminal of the voltage drop across that J6 ohm coil is on the dotted side, okay? And we're going to follow I1 around. So if we follow I1 around, the first thing that we're going to see is actually that positive polarity terminal of that J6 ohm coil, right? So we would have, let me just write a note here, AVL around mesh 1. We would have J6 ohms times I1. We also have to include our mutual inductance because we have magnetically coupled coils, right? So the impedance of our mutual inductance is J2 ohms. What's the current that's flowing through the dotted terminal of our coupled coil? So when I say the coupled coil, I'm talking about the J20 ohm coil. I2, right? So the reason why I chose to define my mesh currents as flowing into the dot is so that I can force these two things to be positive and not have to worry about messing up signs, okay? So it seems awkward for sure, but there was a method to that madness. So if we define our current as flowing into the dot and we define the positive polarity terminal of the voltage across that 6 ohm coil is at the dot, everything's going to come out with a positive sign. Okay. The next impedance I see is my minus J20 ohms. So I'm just going to do plus negative J20 times I1 and then plus 10 ohms times I1 plus 50 angle 0 degrees volts is equal to 0. And now I've completed that loop. So before we algebraically rearrange this guy, let me scroll down so we can try to see that equation and the circuit at the same time. Does anybody have any questions, comments, or concerns about where any of these individual portions came from? Brandon. Why wouldn't the J2 be negative? Okay, so fantastic question. So when we are determining the sign on the mutual inductance portion of our voltage, right? The first thing that we do is we check to see if the positive polarity terminal of our voltage is at the dot or if it's at the undotted terminal. So in this case, it is at the dot, right? Now we look to see if the current that is flowing through our secondary coil is flowing into the dot of the secondary coil or into the not dot. In this case, our current is flowing into the dot. So if we have positive polarity terminal at the dot and current flowing into the dot, we get plus signs. Any other questions? Okay, so if we look at this equation that we just wrote for our Kirchhoff's voltage law representation around mesh one, the only thing that we don't know is that quantity I2. So all I'm going to do right now is just algebraically rearrange and solve for that quantity I2, right? So I'm going to say that our mesh current I2 is going to be equal to, so I'm going to move everything over to the other side. So that's going to look like, let's see, minus J6 ohms times I1. And then I'm going to have minus negative J20 ohms times I1. So let me just put some check marks here. So I've moved this guy over to the other side of the equal sign. I've moved this guy over to the other side of the equal sign. I'm going to have minus 10 ohms times I1, and then minus 50 angle 0 degrees volts. And then I'm going to divide all of this by J2 ohms. So all four of these terms were moved from the left-hand side of the equal sign over to the right-hand side of the equal sign. And then I divided through by that factor of J2. And now I'm just going to combine some things to pretty this up a little bit, okay? So I'm going to write this as negative I1 because there's a common factor of a negative sign, actually, and I1 in all of those terms except for the 50 volts. I'm just going to add these guys together. So J6 plus minus J20 is going to be minus J14. And then I've got my 10 ohms. So I'm going to do 10 minus J14. For what it's worth, that's literally just my primary loop impedance minus 50 angle 0 degrees volts divided by J2 ohms. And now this will be a little bit easier for me to put into my calculator. So I personally am storing that what we solve for as I1 in my calculator is X. And so now what I'm entering into my calculator is negative X times 10 minus 14I minus 50 angle 0, all divided by 2I. And I wound up getting a current of 0.996. So let's call that 0.1 with an angle of positive 175.198 degrees amps for I2. And I'm storing that as Y. So before we move on from this step, does anybody have any questions, comments, or concerns about what we did here? Everybody's okay with all of the signs, the algebra, and all of that kind of good stuff. Okay. So circling back around, now that we know what our mesh currents I1 and I2 are, how would we go about solving for V out? We talked about this a few moments ago when we introduced the problem, but let's, revisit it. Anybody have any thoughts on what we'd do here? Exactly right. So it's just going to be, we're using Ohm's law. So I'm going to do it over here, if that's okay with you guys. So V out is going to be negative I2 times 50 ohms, where that negative sign out front comes from the fact that the current is flowing into the negative polarity terminal as we have defined that voltage V out, okay? So since I put I2 in my calculator as Y, I'm just going to do negative Y times 50, and I wind up getting 4.982 with an angle of negative 4.802 degrees volts. Okay. So that is my phasor representation, but I asked for a time domain signal. So we go back to the time domain by just doing the opposite of what we did to turn this 50 cosine 2000t plus 0 degrees into this guy. So we're going to keep the magnitude, we're going to keep the phase angle, and now we're just going to add in a cosine 2000t, okay? So V out as a function of time is just going to be 4.982 cosine 2000t minus 4.802 degrees volts. Let me make that closing parentheses look less like a backwards letter C. So how did you guys feel about this problem? Wasn't too bad. Pretty darn similar to what we did in the previous examples when we were deriving everything. The only quote unquote weirdness that we really dealt with was the fact that all of our currents were in the opposite direction from the previous examples that we worked with. So let's talk about that really quickly, okay? So this isn't something that is intuitively obvious, but this whole dot convention is all about um, the physical orientation of the windings of the coils, okay? So let me just do this as an aside here thing, okay? Well, let's call this dot convention revisited. So I'm going to try to draw a picture here. So bear with my artistic ineptitude. Um, so this is a section of core material like we've seen before, and I'm going to wrap a coil around it, okay? So here's my first coil. Like so. And here's my current I1, like so. And based on the direction of the winding of this coil and the current that's flowing through it, I know that the flux that's generated by this coil is going to be in the up direction, right? That's just from the right-hand rule. So if I draw a second coil, let's put it down here. If I draw my current I2 flowing in this way, what is the direction of my flux generated by coil 2? Also up. So since these two fluxes are in the same direction, they would add together, okay? So what our dot convention effectively represents is a case where, hey, if the dots are on the same side, the fluxes add together. And if the dots are on the opposite side, the fluxes subtract from each other. So if I have this situation and I have this situation, now essentially my dots would be down here and down here, and my fluxes would be oriented down in both cases, but they'd still add together. So essentially, we have the exact same situation. Our fluxes are adding together. So there are two different configurations that we could have that are going to cause the dots, the fluxes to add together. But in both cases, the dots are either both on top or both on bottom. And so pretty obviously, when we have the situations where they're subtracting, there's going to be two situations, but on both cases, the dots are going to be on the opposite side. So realistically, with that last example problem, we could have just decided to say like, hey, I know my dots are on opposite sides. That's the exact same thing as this. And then we have almost exactly the same example problem that we worked from last Thursday, just with different numbers. There's nothing wrong with swapping both of the dots to make our lives easier. Another way that we could potentially think about things as well, just for what it's worth, is if we have a situation like this, if we flipped either the primary completely upside down, or we flipped the secondary and everything connected to it completely upside down, this would give us a situation where the dots are on the same side. So we can actually manipulate our circuits to make it look like things that we know how to deal with if we're uncomfortable with remembering all of the rules for dots are on the opposite side, this, that, and the other. We just have to make sure that we remember to flip literally everything. So if there's a defined current or something like that, it winds up flipping directions. The voltages flip polarities, etc. But everything has to be flipped over. But you can literally think of it as physically just twisting that part of the circuit upside down. So just as a heads up, sometimes that is an easier way to look at things when it's complicated and you have two separate individual magnetically coupled systems like we do in a transformer. Okay. All right, so let's look at problem 2 here. Okay. So this is a case, just for what it's worth, where we couldn't really manage to flip anything upside down to fix things, simply because we've got this extra connection down here that's preventing us from twisting the circuit, okay? This is very similar to the second example problem that we worked in class last Thursday. But instead of doing a bunch of circuit analysis here, I'm really just interested in what the equivalent impedance of this is going to be. So can we apply the equivalent transformer model to simplify this thing and find some equivalent impedance for the whole system, okay? So I'm going to start us off. I'm just going to put kind of a box around the transformer. And I'm putting these little circles to denote where the terminals of the transformer are so that when I redraw things, I'll know how to reconnect stuff, right? I'm going to call this guy terminal A. This one is going to be B and D, and this guy over here will be C, right? So redrawing this guy, here I have uppercase terminal A, my 8 ohm resistor, my minus J3 ohm capacitance. This is lowercase terminal A. Down here is going to be lowercase terminals. Let me just put it off to the side. BD. Over here to the right, I'm going to have lowercase terminal C. And then continuing my connections over here, I have my minus J5 ohm capacitance. Here's a 15 ohm resistor. Here's a 4 ohm resistor. And then over here is uppercase B. So when I do problems like this, where I'm replacing a portion of a network with its equivalent circuit, I like to imagine in my head that I'm literally removing that network, transforming it, and then connecting it back to the exact same set of terminals. So that's the way that I make sure that I always reconnect things properly, okay? So if we go back to our notes, our transformer equivalent circuit, and this would be our T-shape transformer equivalent circuit, would be something like this, where we'd have some impedance Lx between our A and essentially our neutral. We'd have some inductance Ly between C and neutral, and we'd have some inductance Lz between our B comma D terminals and neutral. So I know that I'm going to have 3 impedances here connected this way. And now I just need to figure out what those impedances are. Well, if we recall, so in this particular case, we know, or actually let's go back to the fundamental thing, right? So we know that Lx is L1 minus M, Ly is L2 minus M, and Lz is M. This was for the case, though, where the dots were on the same side. What do we do when the dots are on opposite sides, like the situation that we're given? Flip the sign on M, okay? So instead of having L1 minus M, this is going to look like L1 plus M, L2 plus M, and then that'll look like negative M, okay? So for us, this guy is L1, this guy is L2, and this guy is M, right? So L1 plus M is going to look like J6 plus J3 is, sorry, J9 ohms. Okay. For Ly, we're going to have J9 plus J3 is J12 ohms. And then for LZ, we're going to have negative times J3. So that's just minus J3 ohms, like so. And now we could probably simplify this network a little bit more if we were so inclined, because I see these 3 elements are simply now connected in series. These 3 elements are connected in series, and these 2 elements are connected in series. So I could simplify this by saying that I have some generic impedance with a value of 8 plus J6 ohms here. So that's just 8 ohms minus J3 plus J9. Down through this path, I have an impedance of 4 minus J3. And across this path, bless you, I have an impedance of 15 plus J7. Bless you again. So with that simplification, it should be fairly straightforward for us to be able to calculate this equivalent impedance, right? So what should it look like?
A plus J6 ohms plus 4 minus J3 ohms times 15 plus J7 ohms. Over the two guys together.
Exactly right. So the two impedances on the right are connected in parallel, and then that's in series with the 8 plus J6 ohms. Great job. And so if we put this into our calculator, 8 plus 6i, and then 4 minus 3i, 15 plus 7i. I typed this in correctly, 12.649 with an angle of 19.795 degrees, or in rectangular form, 11.902 with, plus J 4.284 ohms. All right. So the last example problem that we have for today is this situation here, where we've got some time domain currents flowing into different transformer configurations. And our ultimate goal is to find the energy stored in these systems. So we haven't talked about energy storage in a transformer just yet. So let's circle back over to notes and kind of figure that out. Okay. So and for what it's worth, this is a topic that you will revisit in your ELET 360 class next spring, because this concept of um, energy stored in a transformer is actually part of the electromechanical energy conversion process, that is part of how relays work and how induction motors and synchronous machines and brushed DC motors and all of that kind of stuff work as well. So this is going to be revisited in your later classes, just as a heads up. So let's say that we have a system where we've got a transformer, and we're going to start with our dots on the same side. Okay. So this is going to be some inductance L1. And then here is some inductance L2. Here's our mutual inductance M. Like so. And I'm going to define things for now such that our current I1 is flowing into the dot and our current I2, let me write it above like I did for this guy, is flowing into the dot. Okay. So towards the end of our last class meeting, we learned, and we just practiced this a moment ago, that we could convert this system into an electrically equivalent T network that might look something like this, right? So here's my inductance L sub X. Here's my inductance L sub Y. I'm sorry, that should be L sub Z. And here's my inductance L sub Y. And our current I1 was defined as flowing into the top left terminal. So it'll still flow into the top left terminal. Our current I2 was defined as flowing into the top right terminal. So it'll still be defined as flowing in to the top right terminal as well. So my question to you guys is, what's the current that's flowing through this inductance LZ? I1 plus I2. Absolutely right. Okay. Now, we know also that we can express those inductances LX, LY, and LZ in terms of our transformer inductances L1, L2, and M, right? And again, we just did this a moment ago. So LX is simply L1 minus M, Ly is L2 minus M, and Lz is just M. Okay. So I can say that the energy stored by the impedance L sub X, so I'm just going to call that W sub X as a function of time, is going to be 1/2 times L sub X times the current flowing through that inductance L sub X, which is simply I1 squared. Did you guys learn the energy storage equations for capacitors and inductors back in your circuits one? 1/2 Li squared, 1/2 CV squared. Those sound remotely familiar? Yeah, so that's all we're doing here. We have an inductance, so the energy stored by that inductor is 1/2 Li squared. And I'm just using the subscript X to denote which inductor we're interested in. And I'm using, in this case, the subscript 1 to tell us which current we're following. Okay. So from here, it should be pretty easy for us to just expand this thing out, right? So we would wind up having 1/2 L1 minus M times I1 squared. And that means that we would have a factor of 1/2 L1 I1 squared minus 1/2 M I1 squared. You guys okay with that? Okay. So if we repeat this process, I'll do W's Y over here. We'd start with 1/2 Ly times I2 squared, which would look like 1/2 times L2 minus M times I2 squared. And then lastly, we would have 1/2 L2 I2 squared minus 1/2 M I2 squared. Okay. Now we can figure out what's going on with inductance WZ. And so that's going to be simply 1/2 LZ. And now I have a total current of I1 plus I2. So this is going to look like I1 plus I2 quantity squared like so. Well, we know that LZ is simply M. So that's going to look like 1/2 M. And now I'm going to FOIL this thing out, right? So I'm going to have a factor of I1 times I1. So that's going to look like I1 squared. Then I'm going to have twice I1, I2. And then lastly, I'm going to have I2 squared, like so. And now I'm just going to break this thing down like I did the others. So that would be 1/2 M times I1 squared plus 1/2 M times I2 squared. And then I have a factor of 1/2 times 2, so those guys cancel each other out. And I'm just left with M times I1 I2. So this is the energy stored in each individual inductor that forms our transformer, essentially. So hopefully I'm not stretching too far here, but I believe that we could find our total energy stored by our transformer by simply adding these results together, right? So that W total as a function of time is just Wx plus Wy plus Wz. And I want us to observe something real quick here. So Wx has a factor of minus 1/2 M I1 squared. Wz has a factor of plus 1/2 M I1 squared. So those guys are going to wind up canceling each other out. Similarly, Wy has a term of minus 1/2 M I2 squared. WZ has a term of plus 1/2 m I2 squared. So those guys are going to cancel out, and all that's going to survive is 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus m times I1 times I2. Excuse me. So we derived this with our currents flowing into our dots. So if we had a case where the current was flowing into an undotted terminal, or one of the currents was flowing out of the dot, what do you think would wind up happening? Which part? Or all of it? Just the M. Exactly right. Yeah. So if one of the currents is in the opposite direction, or one of the dots gets moved to the opposite side, we would simply replace positive M with negative M. I know that this is a little bit more difficult to wrap our heads around because both the current direction and the dot location are important. So I'm just going to summarize this in a table without deriving everything over and over again. Okay. So essentially, when we have this situation, actually, let me put it here. So here's L1 dot L2 dot I1 flowing in and I2 flowing in. This is literally what we just derived. Oh, and here's M. Then we have W total is 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus M I1 I2. Okay. If we have this situation, where our dots are on the same side, we define I1 as flowing in and I2 is flowing out, then we would have omega total is, or excuse me, W total is 1/2 L1 I1 squared plus 1/2 L2 I2 squared minus M I1 I2. If we have the situation where we have dots on opposite sides, So here's L1 dot on top. Here's L2 dot on bottom. There's our mutual inductance. I have I1 flowing in here and I2 flowing in here. If we think about flipping the secondary upside down, that would be the situation where dots are on the same side and I2 is flowing into the undotted terminal, or essentially out of the dotted terminal. That means we're going to have the exact same thing that we had just a moment ago, right? Where W total is 1/2 L1 I1 plus 1/2 L2 I2 squared, excuse me, minus M I1 I2. And the last case that we'll go through is dots on the opposite side, and then current I1 flowing in and I2 flowing out. And so that would look something like this. So here's L1 dot on top. Here's L2 dot on bottom. Our mutual inductance M. Let's have I1 flowing in, I2 flowing in. And like I talked about earlier, oh, sorry, I2 should be flowing out in this case. If we flip this guy upside down, we would see a system where dots are on the same side. The current I1 is flowing into the dot, and the current I2 is flowing out of the undotted terminal, which is the same thing as flowing into the dotted terminal. So that's really just the situation that we started with, where everything gets a plus sign. Okay. So with these four cases in mind, we should be able to determine the amount of energy stored in any possible transformer configuration, right? So dots on same sides, currents flowing in and out, dots on opposite sides, currents flowing in and out. Those are the only permutations that we can ever possibly have. Okay. So let's wrap things up today by looking at these two particular example problems. Okay. So in both cases, we are asked to determine the total energy stored by the transformer in network A at T is equal to 1 millisecond, and the total energy stored by the transformer in network B at T is equal to 1 millisecond. We are given our coupling coefficients of K instead of our specific mutual inductance. So how do we use that information to find our mutual inductance? If we go back to our notes from last Thursday, if I'm recalling correctly, I guess I could just look in front of me. We would find that M is simply K times the square root of L1 times L2. Okay. So when we have a K value of 0.6, and then that is going to be multiplied by the square root of 2 times 1. I get, in this case, M is equal to 0.8485. So let's call that 849 henries. And in this case over here, we would have 0.8 multiplied by essentially the square root of 2 times 2, which is just 2. So that should be 1.6 henries. So now, in order to make this a little bit easier on us from a mathematical perspective, I want to find out what the value of I1 is at our time of interest and what the value of I2 is at our time of interest so that we can just plug in numbers and not have to worry about big, gross mathematical equations, right? So let's figure out what I1 at t is equal to 1 millisecond is, okay? So if I look up here, it's going to be 8 cosine 377. Actually, let me put a square brace here. So this 377 is our angular frequency, omega. It is measured in radians per second, okay? If we put in our time of 1 milliseconds, which I'm going to choose to write as 0.001 seconds, if I have something in radians per second and then I multiply it by something in seconds, what do I get? Radians, okay? I'm going to leave some space, and then over here I have minus 20 degrees, okay? So is a degree and a radian the same thing? No, okay? So if I just threw this into my calculator, I'm going to get a wrong result. So I either need to convert 20 degrees into radians, or I need to convert that 377 times 0.01 into degrees. Now, I don't know about you guys, but 99% of the time, my calculator is left in degree mode, okay? So in order to convert this from radians to degrees, I'm going to multiply this by a factor of 180 degrees over pi. Because there are 2 pi radians in a circle containing 360 degrees, which means there is 1 pi radians in half a circle, or 180 degrees. So now I can just throw this into my calculator, right? So I would have 8 cosine 377 times 0.001 times 180 over pi minus 20 degrees. And I wound up getting a current of 7.99687 amps. And I'm going to store that in my calculator for what it's worth as X. Pretty similarly, I can figure out what I2 is doing at t is equal to 1 millisecond in a similar fashion, right? So I've got 4 cosine, actually, that should be in milliamps. Okay. So 4 cosine 377 radians per second, 0.001 seconds, 180 degrees over pi minus 50 degrees. And when I throw that into my calculator, I get 3.518611 and some change. So I'm going to put this in my calculator and store it as Y. Okay. And from here, it should be pretty easy to literally just plug and chug, right? So let's look at this first case, okay? So in this first case, dots are on the same side, and I1 is flowing in, and I2 is flowing out. So what should our energy storage equation look like? The M is going to be negative. Absolutely right. So WA at 1 millisecond is just going to be 1/2 L1 I1 squared at 1 millisecond plus 1/2 L2 I2 squared at 1 millisecond minus M I1 at 1 millisecond I2 at 1 millisecond. So I'm just going to throw this into my calculator real quick. So 1/2, so 0.5 times L1, which is 2 henries, times I1 squared, so that's just x squared, plus 1/2 times L2, which is 1 Henry, times I2 squared, which is y, minus my M of 0.849 times x times y. I got an answer that's close but slightly off. I'm going to write it down and then I'm going to double check. 41.833, and that would have been in microjoules. But let me just double check some things real quick just to make sure. 7 point, sorry, what? Okay, yeah, I feel like I typed something into my calculator wrong, so that's what I want to check out real quick. So I've got X and Y stored correctly. Let me just double check. 0.6 times the square root of 2 times 1. So 0.5 to x squared plus 0.51 y squared minus x times y times z. There we go. Yep. I got 46.264 and some change this time. So I must have typed something in slightly wrong. Ricky, what's up?
Do you just like ignore the 1 millisecond, or do you actually like factor it into that?
So the 1 millisecond is this part right here. We plug the 1 millisecond in to calculate those currents. No. So I'm saying I1 evaluated at 1 millisecond. So the value of that current at 1 millisecond squared, the value of I2 at 1 millisecond squared. So I'm literally just substituting in these values instead of having to put out that whole expression up here again and again and again. So yeah, so this guy right here is not multiplying by 1 millisecond. It is evaluating that function I1 at t is equal to 1 millisecond, which is what we did in the previous part to set things up. Okay. For part B, we've got a situation where we have dots on opposite sides, current flowing in to our first coil and current flowing out of our second coil. So what do you think this is going to be? It's going to be plus M, because essentially we have current flowing into not dot on both sides. So it's going to be plus. So WB at 1 millisecond is going to be 1/2 L1 I1 squared evaluated at 1 millisecond plus 1/2 L2 I2 at 1 millisecond squared plus M I1 I2. And so if I put this into my calculator, I have 0.5 times 2 times x squared plus 0.5 times 2 times y squared plus 1.6 x times y. And I got 121.351 microjoules. Sorry, that should have been joules as well. Just for what it's worth, let's make sure, like I know the units are joules, but I want to make sure you guys understand why the units are joules really quickly. So we have inductance is measured in henries, where a henry is a volt second per amp. And then we have current squared, right? So that's amps times amps. And that's what we're going to have in each of these cases. So pretty obviously, this amp in the denominator cancels this amp in the numerator. So we're left with volts times seconds times amps. Well, what's a volt times an amp? A watt. And what's a watt times a second? A joule. Yeah. So just wanted to make sure you guys are aware of where the units are coming from. All right. I think that's enough out of me for today. We've gone through the ICA. We've covered all of the different conditions that we could possibly have for energy storage. So I'm gonna go lock myself in my office and grade you guys' tests and stuff. So, if you have any questions about anything, goodness gracious, I would obviously be more than happy to answer them. If not, I'll see you guys next Tuesday where we'll start talking about ideal transformers. Yes, sir.